If you rank the most habitable places in our solar system, Venus lands pretty low, with surface temperatures hot enough to melt lead and sulphuric acid rain. And yet it may have just jumped to the front of the pack. In fact, we may have detected the signature of alien life, Venusian life, for the very first time. Our searches for life beyond Earth have tended to focus on the Martian subsurface and the ocean moons Enceladus and Europa, and even the methane lakes of Titan. And yet the horrible hellhole that is the atmosphere of Venus has just yielded perhaps the most exciting lead for extraterrestrial life. Arguably, it's our only lead, the faint signature of the chemical phosphine in Venus's atmosphere, which may have been produced by living organisms. I joked that the weirdest end to this very weird year would be the discovery of alien life. Let's see if 2020 can make up for itself. Now, before we get to the evidence, let's talk about Venus. It's the brightest thing in the sky besides the sun and the moon, hanging just above sunrise and sunset. It's bright because it's close and it's big at 90% Earth's diameter, and it's our closest planetary neighbour. In many ways, it's Earth's twin. It's even inside the band around the sun where liquid water is possible, the so-called habitable zone. But for the longest time, Venus was thought to be among the least habitable places in the solar system. See, Venus has what we call a runaway greenhouse effect. Its atmosphere is 100 times the mass of Earth's, and mostly carbon dioxide. This traps so much heat that the surface of Venus reaches a temperature hot enough to melt lead, and with a pressure that would crush most submarines. That atmosphere also sports a permanent thick layer of sulphuric acid clouds. So yeah, when we realised just how awful Venus was, our telescopes and our hopes for finding ET swiveled outwards to the outer solar system, Mars, Enceladus, Europa in particular, and ultimately to planets around other stars. But Venus was not ready to give up our attention so easily. Our landers and orbiters, Venera, Pioneer, Magellan, caught hints of unusual atmospheric chemistry. Various sulfur-bearing molecules were out of the expected equilibrium quantities. But non-living or abiotic processes like volcanism could still explain these. The other weird thing is that the clouds of Venus appear to absorb the sun's light in a weird way. More short wavelength visible and UV light is sucked up than expected, leading to the yellow colour of the clouds and dark patches that change over time. This could be due to dust churned up from the surface, or it could be gigantic colonies of microbial life. Although the surface is completely hellish, at around 50 kilometers altitude, both the temperature and pressure are close to those at Earth's surface, with the only problem being that pesky sulphuric acid rain. But compared to the death zone of Venus's surface, it's a paradise, and we talked about the possibility of human cloud city settlements in a previous episode. In 1967, Carl Sagan and Harold Morowitz were among the first to suggest that life might exist permanently aloft in Venus's relatively habitable upper atmosphere. These guys speculated about both microbes and larger creatures, alien gas bags, perhaps supported by inbuilt hydrogen balloons. But all these ideas were still pretty fringe. The attention of ET hunters remained focused outwards. One of the most promising avenues in the search for life is to detect so-called atmospheric biosignatures, chemicals in a planet's atmosphere that are very hard to explain without the presence of life. There are lots of ways to do this, for example seeing the effect on a star's light as it passes through its own planet's atmospheres. Another possibility is to look for the absorption of the planet's own light as it emerges from deep within its atmosphere. This can be done at far infrared and sub-millimeter radio wavelengths where the star's own glare doesn't kill the signal. One possible biosignature in this range is phosphine, which absorbs photons at around 1.1 mm wavelength. Phosphine is produced in abundance by some microbes, but not so easily produced by non-biological processes. A team of researchers, led by Professor Jane Greaves, mostly out of the United Kingdom, decided to explore phosphine as a possible biosignature. They thought they'd take a look at Venus using the James Clerk Maxwell telescope more as a control to help guide their studies of planets beyond our solar system, but not really expecting to see anything so close to home. But to their extreme surprise, they found phosphine. The team followed up with ALMA, the Atacama Large Millimeter Submillimeter Array, and confirmed that there had to be phosphine in the upper atmosphere of Venus, vastly more than expected. So, there are two big questions here. Is the detection of phosphine real? And if so, how likely is it that the phosphine came from life? Well, the fact that both JMCT and ALMA detected the feature makes it pretty convincing that it's real, although there's still a chance that both observatories just happened to see a dip in the exact spot where phosphine produces an absorption line. Follow-up observations will confirm or refute this pretty quickly, but the detection is looking pretty solid at this point. Okay, assuming it is real, does this mean we've found life? Well, let's first discuss why the presence of a simple molecule might get people excited about the possibility of life. So, phosphine is a tetrahedron, a pyramid or D4 shaped molecule with 1 phosphorus and 3 hydrogen atoms. It's a common byproduct of living metabolism, although it's also highly toxic. Now, you don't need biological processes to make this stuff. It can form anywhere that you might have free phosphorus and hydrogen atoms. That means anywhere that the more stable phosphorus and hydrogen containing molecules might be broken apart. For example, it's formed deep beneath the surfaces of Jupiter and Saturn and carried to the surface. We've spotted the characteristic absorption features of phosphine in the two gas giants, but no one screamed life because there's a clear mechanism for producing that phosphine by abiotic processes. So why the excitement with Venus? Well, although phosphine can be produced in a number of different ways, it rarely lasts long, no matter how it's made. The stuff is very quickly oxidized, particularly in atmospheres like Venus's. That means something on Venus is making phosphine faster than it can be destroyed. On Venus, there are a few ways to make the stuff. You definitely get some in the extreme heat and density near the surface. You might get some produced by lightning strikes in the cloud layers or by cosmic rays hitting the upper atmosphere. Most of the non-biological production is likely to happen at the surface though, and would take many years to diffuse to the upper atmosphere. However, the scientists calculate that almost all of the phosphine would be destroyed in that time. The abiotic production rate of phosphine is expected to be 10,000 to 1,000,000 times too low to produce the amount of phosphine that was observed. So we're left with two possibilities. Either there's some unknown non-biological process that produced this phosphine, or Venus has life. Honestly, the former still seems the more likely because, well, it's never aliens until every other possibility is ruled out. But this may be the most promising lead to extraterrestrial life we've ever had, so let's talk about what that life might look like. Almost certainly it would be floating microbes like Sagan and co. talked about half a century ago. But the requirements for life in the clouds of Venus are pretty strict. The entire life cycle would have to remain in the regions with survivable temperature and pressure, and the critters need to somehow survive the crazy acidity. Sarah Seeger from MIT and collaborators propose a life cycle that might just do the trick. Firstly, they assert that these critters are microbes living in tiny droplets. Liquid environments are universally thought to be essential to life, and in the extreme dryness of the Venusian atmosphere, free-floating microbes would quickly dry out. But those droplets would be mostly sulphuric acid, maybe 85% concentration with the rest water. By comparison, the most extreme extremophiles on Earth can survive in pools with something like 5% concentration of sulphuric acid in the Dalal pools in Ethiopia. So these Venusian microbes would have to be very different to anything found on Earth. These droplets can only exist in a narrow range in the atmosphere. Droplets are expected to form at a particular height, but as they find each other and grow, they begin to fall back down into the crushing oven of the lower atmosphere where they quickly evaporate again. So how does a droplet-dwelling organism survive this? Seeger and co. have an idea. What if the microbes enter a resilient spore state as their droplets descend and dry out? Earth bacteria can transform into dormant states in adverse conditions, bacterial spores. We previously talked about how these spores can survive crazy situations, including the vacuum of space and the extreme temperatures and pressures of meteor impact or atmospheric re-entry. So what if Venusian microbes pass through such a spore state in the lower atmosphere? The life cycle would look like this. Microbes are in a metabolic state in sulphuric acid droplets in the upper atmosphere. Those droplets find each other and grow. Perhaps microbes multiply in this phase. As they fall and their droplets evaporate, they enter the spore state. These spores are extremely tiny and light, so they float in the haze below Venus's cloud banks. Updrafts then carry the spores into the temperate range once again, where the spores act as nucleation centers for new droplets to form around them, at which point they become metabolically active again. And churn out a bunch of phosphine, I guess. Okay, nice story. The main stretch here is the whole sulphuric acid thing. We just don't know if life can exist in those conditions. An important point here is that Venus's hellish conditions are relatively young, perhaps only around 700 million years old. And before that, it's likely Venus had oceans of liquid water. Any life forms in the atmosphere today must have evolved from presumably much more sensible critters that existed prior to the runaway greenhouse effect. Could microbes really evolve to withstand the transition from a watery to a sulphuric acidy environment? Well, I guess we're about to find out. And how exactly will we find out? Well, the first thing is to confirm the presence of phosphine with more observations. The previous observations were relatively brief, but there's now motivation to point our telescopes for much longer at Venus. We'll need to look for other phosphine absorption features also, and for entirely different biosignatures. But ultimately, we're going to want to go to Venus to search for life signatures there, or even better, to bring samples back to Earth. NASA is about to decide between two proposals for the next mission to Venus. Neither mission has a direct life detecting instrument, but that might change given these developments. However, it may be time to refocus our solar system explorations. Ultimately, we want to bring back samples of the Venusian atmosphere to actually get microbes under a microscope, if they exist. The discovery of alien life in our nearest planetary neighbour would totally change our calculations about the frequency of life in the universe. We may be forced to conclude that life is cosmically abundant. 2020 is the year of weird microbes, but this latest one, if it's real, may prove extremely good news, granting us a grander perspective on humanity's place in a life-filled space-time. Hey everyone, a few things before we get to comments. First up, if you're looking for some more great science content, you should check out Overview on PBS Digital Studio's Science and Nature channel, Terra. Overview is hosted by Joe Hansen from It's Okay to Be Smart and combines mesmerizing drone footage with deep science storytelling to reveal all the things shaping our planet from the 10,000-foot view. So head over to Terra and make sure you politely tell them Spacetime sent you. Next up, I want to send a huge thank you to everyone who helps us out on Patreon. As always, your contributions make a huge difference. But today, an extra big shout out goes to Scott Gray, who's contributing at the Big Bang level. Scott, thank you so much. We've used your contribution so far to bake a nice apple pie and send it to welcome our Venusian neighbours to the solar system, or at least into our awareness of their existence in the solar system. We look forward to neighbourly relations with the gentle Venusian gasbag civilization, and ultimately to ally with them in war against the cosmic string entities in the heart of the sun that we discussed recently. So Scott, I guess thanks for contributing to the future ascendancy of humanity. Okay, last week we talked about post-quantum cryptography, possible solutions to the impending cryptography cracking powers of quantum computers that don't themselves require quantum technology. We were delighted to find several crypto geniuses in our audience who called us out on a few errors. First up, Mina86 pointed out that our use of mixing colors as an analogy for one-way functions in RSA protocol is more accurately analogous to Diffie-Hellman key exchange. Now I agree, and we should have been more careful here. Our point was to illustrate one-way functions themselves, but the way we said it could have been interpreted as illustrating RSA, so thank you for catching that. Several of you noticed that we skipped a power of 2 in one of our graphics. we jump from 256 to 1024. I think it comes from my habit of skipping generations of processor in my computer upgrades. I go for every second Moore's law doubling, which leaves my machines basically paralysed about half the time. And the last catch, a few of you noticed that I use the expression factor a prime number, which is dumb because the factors of a prime number are just itself and 1, which I guess you don't need a quantum computer for. What I meant was factoring the product of 2 primes into those primes. Anyway, thanks for keeping us straight. And finally, a few of you expressed your distaste for lattice-based encryption protocols. Really, there were doubts that any salad-based protocols would be meaty enough to resist quantum decryption.